Continuing our exploration of counting units in chemistry, we're going to talk about the mole. So the mole is the standard chemistry counting unit that we want to use. So MOL, it looks like the name of the animal, but it's actually more similar to the word molecule. So if you think of like it's just the first part of the word molecule, the first 4 letters. And so mole is the name of our chemistry counting unit. The abbreviation is the very much shorter MOL. So when we use MOL, that's our abbreviation for this unit. And just like other counting units, the mole is just defined by the number of objects in the group. So 1 mole is 6.022 times 10 to the 23rd objects. That number is called Avogadro's number. Avogadro was an Italian chemist who did some work with counting molecules, so that's why he didn't come up with the number, but we named it after him in his honor because he did a lot of work in this field. And so these ideas, these measurements that came up with is when we're counting units, we'll count them in groups by the mole. And the reason for that, kind of overall, we'll get to is that's a reasonable size. 12 donuts is like a reasonable sized group for donuts. 500 pieces of paper a ream is reasonable for that. 6.022 times 10 to the 23rd molecules is a reasonable number of molecules. That being said, this number is huge. Okay, so just to kind of give you an idea, I've written out some numbers in not scientific notation. So the just 1 million, billion, trillion, keep going up by basically 1,000 times 1,000 each time. So you can get to 1 sextillion, and then you can reach 1 mole. So this is 600 sextillion is the size of the number of objects in a mole. So you can count anything using a mole. Just functionally, it's not useful for anything that's not tiny. A mole of basketballs would occupy roughly the same volume as the entire Earth. So it has never been useful to count a number of basketballs in moles because that's just a ton of basketballs. You need a really, really small object. Here is a chart from a book, another book that I've used, where it just talks about if you had this mole's worth of, an Avogadro's number of any other object, it would just be stupidly large. It's enough snowflakes to cover the entire of the United States up to the tallest skyscraper. If you had a mole's worth of pizza, it would take all 6 billion people were constantly eating pizza. If you ate an entire pizza every 3 minutes, it'd be 600 million years of consuming pizza, millions of years of non-stop pizza eating. We do have more people on the Earth now, but you're still talking when this 6 billion is a little low, but you're still talking about hundreds of millions of years of pizza eating. These are just stupidly large numbers. And because a mole, this number is so big, 10 to the 23rd, that if you're counting any sort of object that's like roughly human size, it just becomes an overwhelming number. You could theoretically count a mole worth of chairs. It would just be too big to use or too big to mean anything. But it works for atoms and molecules because they are so small. So if you had a mole of molecules, it's a reasonable sized sample of matter. So for example, for water, a mole of water molecules is 18 milliliters. Okay, so 18 milliliters, not huge. Here's what 18 milliliters would look like in a graduated cylinder over here. 18 milliliters is pretty reasonable size, pretty reasonable amount of water. And that's the whole point of counting units, to count out an amount that's kind of a reasonable size, right? That a mole is, you have enough in there that's kind of a reasonable amount to deal with. You obviously aren't going to always use 18 milliliters. There's plenty of times where we use way more than that or less than that, but it's kind of the right order of magnitude. That's kind of giving you a reasonable amount of water, certainly a chemically reasonable amount of water that we would use in the lab or something like that. And it's because atoms are so small. You need a lot of them to get that kind of size. So let's work through looking at a problem dealing with moles. So how many molecules are there in 3.6 moles of sucrose? Like always, we want to start by thinking about what do we want. And here we can see we're looking for the number of molecules. We can see that word many. When we're reading problems, we're going to start to see some language that we can kind of piece into. Whenever we see the word many, how many, that implies we want a number of some sort of object we can count. So for example, you would say like how much money, how many dollars. So in this case, how many molecules means we want a number of molecules. So that's another sign we're working in the world of counting. What do we have? Moles. Okay, so we want how many molecules? That is going to be an absolute count, total individual number of molecules. And currently, it's represented by groups of molecules. A mole is a counting unit. Okay, so when we want to ask how can we relate these, it's going to work in the same way when we related individual bagels to total number of or individual bagels to dozens of bagels, right? Going back and forth between that counting by individual objects and counting by groups. So we relate those by the definition of the size of that group of objects. What is the amount in our counting unit? And in this case, it's going to be Avogadro's number, 6.022 times 10 to the 23rd things in a mole. So let's go ahead and see what it looks like when we actually work it out.
How many molecules are there in 3.6 moles of sucrose? So we know we're looking for molecules, and we have moles. Okay. So if we want to set that up, we're starting with our 3.6 moles. Let me switch colors. And then what we're going to end up with is molecules of sucrose. Okay, and so if we set this up, we know down here I want mole of sucrose. Here I want molecules of sucrose. And so the question is, how are these related? And just like we've seen in the past couple of problems, we're looking at a group of objects, some sort of counting group of objects. We want to relate it to individual objects in that group. So the question is, how big is this group? So 1 mole is equal to 6.022 times 10 to the 23rd molecules. One thing you'll note is that mole and molecules, we haven't specified sucrose. It does not matter that I'm looking at sucrose, just like doesn't matter what you're counting. It's 12 of it. Donuts, cars, planets, gnomes, whatever it is, they're always going to be 12. So 1 mole is always 6.022 times 10 to the 23rd molecules. That is Avogadro's number. So we can go ahead and plug that in. 6.022 times 10 to the 23rd. I kind of cheated, that's why I left a lot of space. I knew this was going to be long. Per 1 mole. So we can see that our moles are going to cancel out. We're left with the molecules that we wanted. And we end up with 2.2 times 10 to the 24th molecules of sucrose. Go ahead and separate that out. So we can see we get a pretty number of molecules of sucrose. One of the things we can see when we want to ever be looking here, whenever you are looking for molecules or atoms or ions where you're counting individual atomic or subatomic particles, they're going to be a huge number. This number is massive, right? 10 to the 24th power. So whenever you're dealing with molecules, you should expect a number of this magnitude. Similarly, you never, if you get this kind of number, this better not be grams, this better not be moles, this better not be anything that is a value that we would measure like in day-to-day life. You do not have 10 to the 24th moles. That is more stuff than exists. And so that is just a huge number. These really big numbers should always be followed by molecules or atoms or ions, something like that. And if you ever do get a molecule, you would expect a big number similarly. But this big number is not going to ever be with grams or anything like that, anything that we would measure kind of in our life.
This result that we got for the number of molecules in 3.6 moles is going to be generically true for that number of moles. 3.6 moles, that size of the counting unit is always going to be the same no matter what it is you are counting. So 3.6 moles of sucrose contains 2.2 times 10 to the 24th molecules of sucrose. Similarly, if you had 3.6 moles of, say, iron 2 chloride, FeCl2, if you did that process, Avogadro's number is the exact same definition, you would get 2.2 times 10 to the 24th. The only difference is in what you are counting. You get formula units for that because iron's a metal, that's an ionic compound. You got molecules in the case of sucrose because these are all nonmetals, and that's a covalent compound. So that's just some chemical language in terms of what are you counting? What is the smallest individual object of the compound? If you had an element, say for example just silicon, now your moles are counting atoms. So mole as a counting unit, you're always counting the same number of objects. The question is just, what is our name for that object? Covalent compounds are made up of molecules, ionic compounds are made up of formula units, and elements are made up of atoms. You could also count individual ions. You could count anything like that. Neutrons, protons, any sort of object that you wanted to count, pairs of atoms, anything that you want, however you choose to define it. And so there is a little bit of chemistry you need to kind of parse out when you see based on the formula. Is it a covalent? Is it ionic? Is it an element? So we can always count different things, but the mole number definition is always the same. You'll note that you always get 2.2 times 10 to the 24th. We do also really want to be careful when, say, we are presented with something like this, 3.6 moles of O2. This moles means we are counting O2. That is a whole molecule. It is 2 oxygen atoms in each molecule, but that is what we are actually counting. So if we used Avogadro's number and converted out to individual objects, we'd be counting molecules, not atoms. There's a relationship. There are certainly a number of atoms, that relationship that comes from that 2 right there, but you're still dealing with counting overall molecules. So we do really want to be careful. The mole applies to everything in that formula. So the full, in this case, O2 is what you are counting. Whatever comes after moles, that's the object that you are counting. And I guarantee you this is one of the more common issues of just kind of forgetting what you're actually counting. And so, hopefully, it gives a lot of practice related to these things. We're all going to make this mistake, so let's try to make it earlier and not later. Participation 6.8, question 1. Arrange the following from most to fewest molecules. 3.4 moles SiCl4, 5.1 moles H2, and 1.9 moles C6H12O6. This is the first question on participation 6.8 due Monday, June 8th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, arrange the following from most to fewest molecules. It's 3.4 moles silicon tetrachloride, 5.1 moles of hydrogen, and 1.9 moles of glucose. All right, we got our first question for participation 6.8. Got to watch some more videos, see if we find any more of those questions. I'm sure there's more than one. I'll see you in the next video.